科学的重要性是非常清楚了。没有科学的发展，世界不可能像今天这个样子。未来论坛创建这个科学大奖是一个非常有意义的事情，这是一个了不起的创举。
科学的作用最根本的就是扩展了我们人类对自然界的了解。科学是我们人类知识的边界，其实也是我们生存空间的一个开拓。
所以我们希望呢，这个科学慢慢的成为我们现代社会的一个非常重要的一个文化，会对我们这个中华民族的兴起会起一个非常重要的作用。
科学已经成了我生活中的一部分，而且是生活的一大部分。数学这种美比较，就是有一点阳春白雪的样子，比较抽象的美，然后一种绝对的真理。
很多做科学的人，包括自己在内，是可以从小一直有兴趣，一直到现在，或者一直到将来。
我小时候的理想，就是因为有那个科学的春天，正好在我小学毕业的时候理想就是要当科学家。现在回过头来想想，那时候真是一个很幸运的选择。
它是一种探索，是一种创新，这种探索会是孜孜不倦的，会是勇敢的，甚至有时候是这个寂寞的。
科学跟技术的发展呢，其实是带来人类的文明的发展；技术呢的发展呢，带来的呢是一个渐进性的发展。但是呢，科学的发展呢是一个根本性的、基础性的发展。
我们用的 GPS 都用到广义相对论，都用到这个基本的一些物理原理，所有的一切都是用到科学。
中国最缺的就是那些核心技术，而中国核心技术的提升一定要靠我们中国基础科学的研究的提升。
真正的创新工作的话呢，实际上是制定标准，不是跟着别人标准做。
一个是对在过去20-30年当中，中国在基础科研上面一些有原创性的、有突破性的，是一种充分的认可。这个也就是对将来我们接下来20-30年当中，或者接下来几十年当中，我们现在一批年轻人，就是需要鼓励他们去走原创的道路，鼓励他们去多做一些有突破性的工作。
科学是大国发展必不可少的重要的基础，所以像我们中国这样一个大国，是不可能避开科学而成为真正的一个世界强国。
我们今天有很多企业家的楷模，但是我们今天需要更多科学家的楷模。作为一个这个投资人，我认为他必须有这样的一些远见，同时我认为也有一点责任去贡献更多，不管从资金上面还是从资源上面，去推动这样的一些这个科学前沿的发展。
在这个时间点，我们设立奖励，这更彰显了科技改变人类生活的这个重要性，真正的能够认可那些默默无闻的对社会做出巨大贡献的科学家，可以提升对他们的认知认可，
同时吸引更多的企业家、社会各界人士关注和支持科学家们的工作，促进科学成果的应用转化。
未来科学大奖是来自民间的，将会是国家、政府奖励科学研究、科技创新的有力补充。民间资本的介入，能使中国对科研工作者的奖励更加多元化。
任何一个奖，它的灵魂就是评审，不光是公正，关键还是它的准确性、它的科学性。这个评选的过程中，要借助全世界的各种专家来一起来评审。
我们靠什么规则来达到最大限度的共识，是一个技术性的问题，跟规则的建立是有关系的。我们就是确保每次开会、每次讨论，我们整个规则是得到严格执行的。未来科学大奖能够在今后的多少年里，是越来越得到公众的认可，越来越得到科技界的认可，使得它能够发扬光大，最后变成全世界范围内的人类的共同财富。
我们今天呢是在探索一条路，能够让企业家和科学家结合在一起，通过这种大奖的形式的话呢，给予科学家、给予中国的基础科学的研究呢给予支持。
这样的这个做法呢，完全是自发的。我们确实觉得，一个国家的这个创新能力，对国家的这种繁荣昌盛太重要了。做未来科学大奖呢，也是希望在这方面做一些尝试，
推动中国的科学的这个发展与这个国力能够相称，使中国的这个整体的水平和竞争能力迈向一个新的台阶。
希望未来科学大奖能够成为国内乃至全球最具有影响力、最有激情、最好玩又最具有人文关怀的科学大奖，
成为华人对科学探知上一个里程碑的符号，能够让更加多的中国人通过这个大奖去热爱科学，
把这个科学的精神、对科学的了解、科学的热情传播到你的那个 community、你的那个朋友圈里去。
我们的科学家人才也会层出不穷，我们的全社会的这个科学文化素养也会进一步的提升，
可以激励很多我们将来的青年学生来投身到科学当中。
这个奖项应该像血脉一样往下传。这个背后，我觉得实际上是对一种科学精神一种启蒙、一种传承、一种强化。这样的话，这个科学奖项就不是嘉奖的一个刹那，而是嘉奖的一个时代，甚至是若干个时代。
有一句话叫“以史为终”，我却看到它100年以后的景象。100年以后，未来科学大奖怎么样？那个时候人们会说，诺贝尔奖不要，我们要未来科学大奖。
我预祝100年以后，有一群中国科学家仔细看我们这个录像，然后回顾我们未来科学的大奖如何影响中国科学100年。
Distinguished guests, ladies and gentlemen, welcome to the 2023 Future Science Prize Laureates Lecture, Deep Research Learning and How It Shaped the AI Landscape by Dr. Kaiming. My name is Chen Baihui Clara, a first-year Master of Science in Financial Technology student at the Chinese University of Hong Kong. It is my great pleasure to be your host this afternoon. It is our great honor to have Dr. He with us today, who is a proud alumnus of CUHK and currently a research scientist at prestigious Facebook AI Research. Ladies and gentlemen, please welcome Professor Maihai Shen, Pro-Vice Chancellor and Vice President of Research at the Chinese University of Hong Kong, to deliver a welcoming address. Professor Shen, please.
Distinguished guests, colleagues and friends, ladies and gentlemen, good afternoon. Today, I stand here with tremendous pleasure on behalf of the Chinese University of Hong Kong to welcome you to this special lecture by the winner of the 2023 Future Science Prize in Mathematics and Computer Science, Dr. Kaiming He, who is currently a research scientist at the prestigious Facebook AI Research and will be joining the Massachusetts Institute of Technology's Department of Electrical Engineering and Computer Science as a faculty member in the coming year. In addition to obtaining insights from Dr. He on how his research in the field of computer vision and deep learning has revolutionized our lives, today's event carries another meaning to us, as we are celebrating the remarkable achievements of another member of the CUHK family. For Dr. He is a proud alumnus of the university who received his PhD here in 2011. Dr. He, congratulations on receiving the Future Science Prize. Most importantly, welcome home. I would like to express my sincere gratitude to Mr. Victor Wang, co-founder of Zen Fund and donor of the Mathematics and Computer Science Prize of the Future Science Prize, and members of the Science Committee of the Future Science Prize, Professor Don Song and Professor Kai Li, as well as Ms. Kathy Wu, initiator and Secretary General of Future Forum, for gracing us with their presence today. Your generosity and support have been an important driving force behind scientific discoveries for the benefits of mankind. Established in 2016 by a group of enthusiastic scientists and entrepreneurs dedicated to promoting basic science research in Greater China, the Future Science Prize towards rewards outstanding scientists for influencing China, the world, and the next generation with the spirit of innovative science. It represents the pinnacle of scientific research recognition in the region. It is indeed a privilege for CUHK to host this momentous occasion to acknowledge Dr. He's fundamental contributions to artificial intelligence by introducing deep residual learning. Today's lecture represents a precious opportunity for us to delve into the depths of Dr. He's research and understand its profound social impact. Not only does his groundbreaking research open up new possibilities for the field of computer science, but it also manifests the power of scientific exploration in shaping our future. I'm sure all participants will be inspired by Dr. He's passion for innovation and commitment to pushing the frontiers of human knowledge. Ladies and gentlemen, let us applaud Dr. He's outstanding accomplishments and congratulate him on this well-deserved recognition once again. May I wish you all a very rewarding lecture. Thank you.
Thank you, Professor Shen. Please be seated. It is now my honor to invite Mr. Victor Wang, donor of the Mathematics and Computer Science Prize and co-founder of Zheng Fund, to introduce the Future Science Prize and Dr. Kaiming He's awarded work. Mr. Wang, please.
Ladies and gentlemen, on behalf of the Future Science Prize, I'm very pleased to welcome you to this lecture. Today, we are here to celebrate the work of Dr. He, who was awarded the 2023 Future Science Prize in Mathematics and Computer Science for fundamental contributions to artificial intelligence by introducing deep residual learning. He is a distinguished artificial intelligence specialist, and he received his PhD degree from the Chinese University of Hong Kong in 2011. This is the first cooperation between the Future Science Prize and the Chinese University of Hong Kong. This lecture is particularly meaningful as it is taking place at the Chinese University of Hong Kong, a university that has nurtured many outstanding individuals who have made significant contributions to society. Dr. He is not only one of them, but also a prime example of the university's commitment to excellence in research and innovation. Dr. He's remarkable achievements in AI have not only been recognized by the Future Science Prize, but also by the global scientific community. Today, we have gathered here to pay tribute to Dr. He's outstanding contributions to AI research and development and to honor him for his world-class work. Before I hand the floor over to our proud laureate, I would also like to introduce to you the Future Science Prize, which is a privately funded science award initiated by a group of scientists and entrepreneurs. The Future Science Prize aims to celebrate the accomplishments of scientists who have made extraordinary scientific contributions, mainly in the mainland of China, Hong Kong, Macau, or Taiwan. There is no restriction on the nationalities of laureates. There are three major categories at present, namely the Life Science Prize, the Physical Science Prize, and the Mathematics and Computer Science Prize, with each award of $1 million respectively. The Future Science Prize has been awarded to 35 laureates since 2016. All laureates are highly accomplished, widely recognized scientists whose research has made extraordinary impacts in life sciences, physical sciences, chemistry, mathematics, and computer science. Finally, on behalf of the Future Science Prize, I would like to express my heartfelt congratulations to Dr. He. We believe that his achievements will inspire the next generation of scientists and engineers to pursue excellence in research and innovation, leading to further advancements in AI and related fields. Lastly, I wish today's Future Science Prize Laureate lecture a big success. Thank you.
Thank you, Mr. Wan. Ladies and gentlemen, please welcome Professor Zheng Hongqi, Interim Dean of the Faculty of Engineering at CUHK, to introduce Dr. Kaiming He. Professor Zheng, please.
Chancellor Sam, honored guests, esteemed colleagues, and students here. Thank you for joining us this afternoon at this, the Future Science Prize Laureate Lecture. Today, as the Interim Dean of Engineering, I am most pleased to welcome back to CUHK our engineering alumnus, Dr. Kaiming He. He entered the Department of Information Engineering in 2007 and graduated from CUHK after completing his PhD 12 years ago under the supervision of Professor Xiong Tang. Dr. He shares this year's Future Science Prize in Computer Science and Mathematics. Dr. He has made many highly impactful contributions in the field of computer vision and deep learning. For example, his innovations on deep residual networks introduced the concept of residual learning, transforming the implementation of neural network training. This work was one of the most cited papers, according to Google Scholar, in the years 2019, 2020, and 2021. Residual learning is a fundamental tool for modern deep learning models, contributing significantly to famous AI systems like AlphaGo, ChatGPT, etc. Another of Dr. He's contribution is on the faster region-based convolutional neural networks, which dramatically improve the speed and precision of object detection, and which he further improved by introducing the mask-RCNN, which have found widespread applications in fields as diverse as healthcare, autonomous vehicles, and robotics. It is therefore with great pride that I present to you Dr. Kaiming He, our illustrious alumnus and a pioneer in the field of artificial intelligence. He is a truly deserving recipient of the Future Science Prize. His work has advanced the underlying technology for AI, underpinning the wider emerging applications of AI. I now invite Dr. He to take the stage to deliver the Future Science Prize Laureate Lecture. Please join me in welcoming Dr. Kaiming He back to give the talk about his remarkable achievements.
Thank you, Professor Chen. Please be seated. Ladies and gentlemen, please join me in giving a warm CUHK welcome to Dr. Kaiming He. Dr. He, please.
Thank you for your introduction, and good afternoon, everyone. First of all, I would like to thank the Future Science Prize Committee for inviting me to give this talk. I would also like to thank the Chinese University of Hong Kong for hosting this event. I graduated from CUHK 12 years ago, and it's my honor to give the talk here. Today, I'm going to talk about deep residual learning. If you are working on artificial intelligence or AI today, you may be using some forms of deep residual learning. As a result, you may already be familiar with part of the talk, but I still hope I will be able to share with you some context about the work. If you are new to the field of AI and you are curious about how AI was developed into today's progress, I hope I will be able to share with you some interesting history. So a human can easily recognize the dot in this image, locate its position, and make sense of its outlines. This ability is known as visual perception. Over the last decade, the focus of my research is to enable computers to perceive the visual world like human beings. Actually, long before computers were invented, people had realized that visual perception is an interesting problem. The 19th century physicist Helmholtz had pointed out that the human visual system is making some unconscious inference on visual images. And he was trying to build computational and mathematical models to explain the human visual behavior. And we are luckier than Helmholtz and many other pioneers because we have computers. We can directly test the hypothesis of the models on computers for mimicking the visual perception ability of humans. And it turns out that while visual perception is simple for human beings, it is surprisingly difficult for computers. This is a document from MIT in 1966. In this document, the author attempted to solve the computer vision problem by a summer project. If this project was successful, then it is unlikely for me to join MIT today. Fortunately and unfortunately, after half of a century, computer vision is still not solved. At that time, people had explored artificial neural networks to solve computer vision and other AI problems. These machines are designed to mimic the human brains by connecting many simple units called neurons. And here is an example of how the machines look like at that time. The human brains have tens of billions of neurons, but the machines at that time were not able to achieve this scale. As a result, people had turned to other solutions. The focus of these other solutions was on how to represent the visual objects. These visual representations provide abstractions for the concepts that are common across objects. For example, in the 1970s, people proposed to use curves or cylinders to model the bodies, arms, and legs of humans or animals. In the 1980s and 1990s, people had developed more general and reliable detectors to detect visual representations, such as edges or local features from the images. Now let's discuss what the most successful algorithm looked like at that time. Given an image, we may compute the edges or gradients, and then we can compute their orientation and their histogram. Then we can map them into some digits by clustering. And finally, we can map these numbers into some class labels by a classifier. This methodology works pretty well in some simple scenarios, but it requires humans to introduce different levels of abstractions, such as edges and orientations, and its performance can be limited by the human design of representations. In parallel with this progress, research on artificial neural networks have been advancing over the last several decades. In the 21st century, the usage of artificial neural networks is more popularly referred to as deep learning. This new terminology, deep learning, is a summary of several key ideas. The first idea is to use a set of general operations instead of human design representations. By using the same set of general operations, it is easy to build multiple levels of abstractions. And this is the idea of going deeper. And these operations are learned end-to-end by backpropagation, so the reliance on human knowledge is further reduced. Deep learning models can be trained on larger-scale data, so they may discover patterns and abstractions that are difficult for humans to design. These ideas of the deep learning methodology may be considered as obvious, natural, and even common sense today. But this was absolutely not the case over 10 years ago. At that time, there was a lot of doubt and challenges on using the deep learning methodology to solve problems. Actually, the scopes of these ideas were rather limited 10 years ago. over the last decade, my research on visual perception has largely extended the horizon of the deep learning methodology, and this talk will cover parts of this story. In 2012, a model called AlexNet started a deep learning revolution in computer vision. In this seminal work, it presented an 8-layer neural network for solving a challenging problem of image classification, and it achieved unprecedented accuracy. The community was excited by this progress, and after 2 years of iterations, the depth of the neural network had been doubled. At that time, this trend looked really promising. It looked like if we keep increasing the depth of the neural networks, we are going to get better and better accuracy. But this is the reality. It turns out that after a certain point, for example, 20 layers, the neural networks start to degrade very quickly. And this degradation is not because of overfitting. It looks like these deeper neural networks are just worse models than the shallower neural networks. The community had been struggling with this problem. People had tried various methods to address this problem, including initialization methods, normalization methods, and specific layer-wise designs. But this problem was not solved. This issue was like the clouds over deep learning, analogous to the clouds over physics 1 century ago. Here is a brief overview on the attempts of training neural networks back then. The initialization methods address the issue involving the beginning of training. Without a good initialization, the deeper neural networks may not converge. On the other hand, the normalization methods attempt to maintain the range of neural network activations or representations, preventing them from being too big or too small. Good initialization methods and normalization methods are still required today, but they're not sufficient to train deeper neural networks. In addition to this attempt, people have also tried to carefully design every single layer for a neural network to go deeper. And GoogleNet is one of the most compelling examples of this kind. However, the depth of neural networks was still very limited. In 2015, we showed that deep learning can get way deeper than people might have imagined. We proposed residual networks, or ResNet, which increase the depth of neural networks by 1 order of magnitude. And here is an illustration of a ResNet with over 100 layers. The introduction of ResNet cleared the cloud over deep learning. We can easily train very deep neural networks and get better accuracy. And this largely pushed forward the deep learning revolution. Next, I'm going to introduce what is a ResNet. The idea of ResNet was based on a thought experiment. Given a shallower network, we can always construct a deeper neural network by simply inserting layers. If we can train a good shallower network, then we can have a deeper network that is at least no worse than the shallower network, at least in terms of training accuracy. This is because we can simply copy the layers from the shallower network and set the other layers as identity mappings. So it looks like optimization is not able to find such a solution. It is also not able to find a solution that is better than this one or close to this one. The idea of residual learning is to explicitly introduce the identity mapping into neural networks. In this case, we can let the weight layers fit a residual function, or delta, which is then added to the inputs of the layers. So if the identity mapping is optimal, it is easy to find the solution because the weight can be set as 0. And if the identity mapping is near optimal, it should still be easy to find a solution because the weight can be set as some small numbers. In this sense, residual learning actually encourages neural network to make conservative and small changes. By putting many small changes together, it is possible to learn complex functions, and this is the spirit of going deeper. Interestingly, the idea of using skip connections is nearly as old as the idea of artificial neural networks. This person in this photo is named Frank Rosenblatt. He wrote a book which proposed the multi-layer perceptron, or MLP, in the 1950s and 1960s. And this plot is taken from his book. In this plot, he studied a special case of MLP with a skip connection here. At that time, the neural networks were way shallower, and the value of using skip connections to train very deep neural networks was not realized. Actually, a major value of residual learning is to enable stacking building blocks for creating very deep neural networks. This largely extends the deep learning methodology on using general operations for learning multiple levels of abstractions. People can focus on the design of general operations or the design of general building blocks, and multiple levels of abstractions can be learned by stacking these building blocks. By simply stacking building blocks, we can easily train very deep ResNet and get better accuracy. Here are the results on an image classification dataset called CIFAR-10. Here, the x-axis is the depth of the neural network, and the y-axis is the accuracy. We can see that a vanilla network starts to degrade very quickly, and ResNet can keep improving even after 100 layers. This pattern is observed in almost all datasets. Here are the results on the ImageNet classification dataset. ImageNet was kind of a snapshot of the deep learning progress in those years. And we can see that a deeper ResNet has a better accuracy. It is worth noticing that the ResNet instantiations in this figure, developed 8 years ago, are still the standard baselines in computer vision today. We have shown that ResNet have dramatically different behavior with vanilla neural networks, and we attempted to provide some theoretical understandings on this problem. In summary, we found that while a vanilla network performs a series of matrix multiplications, a ResNet performs a series of additions. And this makes a big difference. In the case of a vanilla network, every single layer performs a matrix multiplication, and here we only show the simplest case without an activation function. Applying this formulation recursively, we can see that the output of a neural network is a series of matrix multiplications. And if we compute the gradient, we can see that the gradient is also a series of matrix multiplications. And this is the reason for the notorious vanishing gradient problem. It is just unstable to multiply many matrices together. Intuitively, if the magnitudes of the matrices are too small, then after many multiplications, the output would be vanishing. It is worth noticing that not only the gradient can vanish, the forward propagation can also vanish. In this case, the information of the input is simply lost. So we need to solve not only the vanishing gradient problem, but also the vanishing forward propagation. This is, in the case of a ResNet, each block performs addition. And applying this formulation recursively, we can see that the output of a neural network is a set of additions added to a shallower input. And this computation can be visualized in this way. Here, x in the top is the input to a neural network, and x on the bottom is the network output. And this computation means there is always a signal that is directly sent from the input to the output of the network. So it is unlikely for the output to be vanishing. The gradient computation has a similar flavor. There is always a gradient that is directly sent from the output of the network to the input of a shallower layer. So it is also unlikely for the gradient to be vanishing. To wrap up the theoretical part, a vanilla network performs a series of matrix multiplications, and the ResNet performs a series of additions. This difference affects how signals are propagated inside the network, which is the key issue in training very deep neural networks. Going deep is the key to the success of deep learning. It allows us to compose basic modules into highly complex functions. The complexity of the neural networks is related to the network's depth and its number of parameters. These deep neural networks can be trained on larger scale data, so it requires less domain knowledge that is specific about the underlying complex functions. This means we can simply use the same set of basic modules to solve different problems. This is why deep learning can provide general solutions to various problems in different fields. Because of the significance of going deep with neural networks, the influence of deep residual learning is far beyond computer vision. In 2016, the groundbreaking AlphaGo attracted public's attention by beating the expert human players. Just 1 year after that, in 2017, AlphaGo was upgraded to AlphaGo Zero, which beat human players without using human knowledge. In the area of natural language processing, exciting progress is also being made. The progress is represented by large and very deep language models, including the transformer architecture, the GPT, and ChatGPT that everyone is using today. The development of more capable neural networks also advances many scientific areas. For example, in biology, the AlphaFold system achieved groundbreaking results in the problem of protein structure prediction. All of these and many other breakthroughs involve some forms of deep residual learning, which can be the original ResNet block or the usage of residual connections. These AI breakthroughs are all based on very deep neural networks, and the usage of residual learning are important for these models to work. Next, I'm going to briefly introduce how these AI breakthroughs are connected to deep residual learning. The game of Go has been considered as a challenging problem in AI. Part of the reason is that there is an exponentially big number of the states of the board. As each location has 3 possibilities, black, white, and empty, then there would be 3 to the power of 19 by 19 states just for a single move. And this is a huge number. However, if viewing the board as a 19 by 19 image, then this is actually a very tiny image. This image can be represented by neural networks that are designed for image recognition, including the neural networks of ResNet. And these representations can be used to guide the moves and actions taken. Based on this philosophy, going deeper is the key to increase AlphaGo's capability. This figure is from the AlphaGo Zero paper. Here, RES denotes residual networks, and they are compared with traditional convolutional neural networks. Here, the comparisons are on LO ratings, and a higher rating means a better performance. So this figure simply shows that ResNet is important for AlphaGo Zero to achieve a high rating. So it is one of the many factors that enable AlphaGo Zero to beat human beings without human knowledge. And the AlphaGo Zero system has 40 residual blocks as reported by their paper. Next, I'm going to talk about the story of going deep with sequence modeling. The applications of sequence modeling include language, speech, audio, and many other scientific problems. A classical method for sequence modeling is the recurrent neural networks, or RNN. Recurrent neural networks are designed to capture long-range dependency in sequential data. However, going deep with recurrent neural networks is a challenging problem. This figure is from a paper which introduced Google's neural machine translation system in 2016. In the left plots of this figure, they show a typical form of a recurrent neural network using LSTM. In the right plots of this figure, they show how they can build a deeper recurrent neural network with the help of residual connections. The paper reported that residual connections are of central importance for their recurrent neural network to go deeper. In addition to recurrent neural networks, people have explored convolutional neural network for sequence modeling. A convolutional layer has a fixed receptive field. As a result, to capture longer context in the sequence, it is of central importance for the network to go deeper. Residual connections are playing an important role in these networks. And here is an example from the WaveNet architecture, which is designed for audio generation. Beyond recurrent neural networks and convolutional neural networks, the most successful methods for sequence modeling today are based on the attention mechanism. Simply speaking, the attention mechanism allows every single item in the sequence to be directly related to every single other items. The resulting architecture, which is called a transformer, is a stack of attention blocks and MLP blocks. Residual connections play an important role here, and it is used in every single block in transformers. Today, transformer architectures are dominant in sequence modeling applications. Generative pre-trained transformer, or in short, GPT, is perhaps the most well-known application of transformers. The goal of GPT is to predict the next word of a text given all the previous words. This task, which is called next word prediction, provides a natural and effective way for generating text. Because GPT is a form of transformers, the residual connections are parts of the GPT architecture. The power of GPT and other language models is shown in their scaling laws. The scaling law refers to the empirical observation that if the size of the model increases, the capability of the model also increases. The size of the model can be increased by using a deeper neural network and using a larger dimension per layer. For example, the GPT-3 model, which is the engine for the very powerful ChatGPT that everyone is using today, is reported to have a depth of 96 blocks, and as each block on its own has a depth of 4 layers, this model has a total of about 400 layers. Residual connections in these GPT models facilitate the training of these very deep neural networks. GPT and ChatGPT are not the only AI breakthroughs in recent years. In the field of biology, AlphaFold is an outstanding AI breakthrough in the area of protein structure prediction. Its goal is to predict the 3D protein structure given an input sequence of amino acids. Interestingly, while this problem involves sequence modeling, the earlier version of AlphaFold used a model similar to an image recognition network, basically a typical ResNet, as shown here. This figure is from the first AlphaFold paper published in Nature in 2020, which shows that the network architecture has 220 residual convolution blocks. This figure is from the latest version of AlphaFold published in Nature in 2021, which represents the state of the art in this area. In this version, the problem is formulated as sequence modeling with an architecture that has 48 transformer blocks. Again, we can see that residual connections are used in every single block. To recap, the philosophy of deep learning involves composing basic modules into highly complex functions and learning representations from data. And this is why deep neural networks can provide general solutions to various problems in different fields. And the framework of deep residual learning provides a simple and effective solution that enables neural networks to get way deeper. And because of the significance of depth in neural networks, deep residual learning is among the most influential work in AI in the last decade. With this, I hope you enjoyed this talk, and I'd like to thank you for attending.
Thank you, Dr. He, for your inspiring and informative lecture. It is the time for us to meet the award recipient. Dr. He, please take a seat. I would also like to invite Professor Xue Tianfan, the Vice Chancellor Assistant Professor of the Department of Information Engineering at CUHK, to join Dr. He and moderate this session. Audiences are welcome to ask questions. When Professor Xue invites you to speak, please use the microphone next to your seat and press the red button to speak. Professor Xue, please.
Thank you very nice to coming, Dr. He, and it's really inspiring talks, and I learned a lot. I mean, already I learned this before, but I learned this again. So let me start with a few questions, then I'll pass to the audience for more questions. So I really like your graph, like I showed in the very beginning, when the deep network becomes deeper and deeper, performance first goes up, then goes down, and people first may think it's overfitting because of like training data. Then adding more data sometimes helps, but still, when it's really deep, it goes down again, then your work actually shows there's actually some optimization doesn't reach the optimal solutions. So there's a kind of basically three factors here: how much data you get, how deep your networks, how complex your models, and how to optimize it. So now these days, because of this like large foundation models, the data's models are much bigger than before. So what do you think might be the kind of like limitations or next steps to improve in these three factors, like data, model complexity, and optimization? Thank you.
Yeah, thank you for your question. Usually we consider going deep and going wide as increasing the capability of the neural network models. Then in machine learning, then there would be a trade-off. That is basically fitting and generalization, which means fitting and reduce overfitting. So today, the most effective method to reduce overfitting, to improve generalization, is just to feed more data. Then how can we fit? How can we memorize or just fitting so much data is an open problem. Then it turns out that this big and deep model are very good and they have enough capability to memorize and fit so much data. Then it turns out that adding more data is the best solution to reduce overfitting. Then moving forward, it depends on whether the return from data will be diminishing. For example, language data were generated by human beings. That means if you write some new text, usually it is not, out of nowhere. You have some, purpose. You have some information that you want to share, or you want to create some new knowledge. So perhaps the information in text data would be much more than many other forms of data. For example, if you take photos, it looks like a photo may have more information, but actually if you think about what you are taking using a phone every single day, perhaps it's just your food or your selfie, that may not add much more information. So that means different type of data may have different levels of information. That increasing the data may have diminishing return at different level of their scales. So I think this would be a future open problem after the return of data has been diminished.
Thank you for very detailed explanation about that, and yeah, that's what's the return of data is a very interesting discussion for future research. And related to this problem, also in your talk, you also mentioned that like this residual learning, or actually in general, all deep learning has now utilized in many places like AlphaGo and also the AlphaFold and all these tasks. So like before, like 10 years or 20 years ago, like when people are doing research, where people are working on each specific small problems and designing algorithms, as you mentioned earlier, hand design everything. Now these days, everything's kind of learned by the more general models can solve all of this kind of problem. So do you think like just foresee in the future trend, will there be like a big pre-trained models that can handle most of the tasks and just fine-tune for each specific task? Or there's still some problems that need like more hand design or like the more specific domain knowledge to solve that? Can you share some kind of like your insights about this?
I think both directions will progress in parallel. So a pre-trained model is basically the by default in NLP, basically. Then in computer vision, the story is a little bit different because people have not come up with a good idea for developing the so-called visual foundation models. This is perhaps because, well, the vision task can be more diversified, and perhaps also more importantly, the languages are the outcome of human intelligence, but the pixels are from the nature. So So these are the different natures between language and images. So then moving forward, I think, well, we also hope the neural networks can handle more problems. Let's say the scientific problems, proteins, molecules, materials, and perhaps deriving equations, doing mathematics, chemistry, and physics. So there are a very large number of different problems. So we hope we can have some general foundation models that can help us to do some general work. But on the other hand, we also hope we will have some specialist models that can help to advance the state of the art in one particular direction.
Yeah, that makes sense. So these two directions we are pushing forward in the future. Thanks for your explanation. So maybe it's time to pass the question to the audience. One thing to mention, because this is more like a technical discussion. So if you have any, let's keep the discussion more technical. If you have any questions about career, we can talk it offline with Mr. Dr. So please, yes, please.
Thank you, Professor Xue, and thank you, Dr. He, for your wonderful talks. And I have two questions. The first is, what is your research focus in the next 3 years? And the second, and the second question is that how to find a research topic that can be published as CPPR best paper. Thank you all. I want to briefly introduce myself. My name is Xu Zhenseng, and I'm also a student, a PhD student from MN Lab. I'm very glad you are here. Thanks.
Thank you for your question. You asked $2 million questions. Let me answer the first one. Okay, what is the first one? The first one is what I'm going to do in 3 years, okay? Okay, good question. Basically everything. Well, computer vision is not solved. So today, NLP is very successful because people can do self-supervised learning on language data. So I have been trying to reproduce this success in the context of computer vision. That means I want to make visual self-supervised learning successful. What is the definition of successful? I want to see the same scaling law as the language models. So I hope if we can just increase the size of the model and increase the number of data, we are going to see a much stronger capability from the vision models. Unfortunately, this is not yet the case. So today, language model is very successful. Vision and language model, so vision plus language, that is also very successful. But this is not yet the case for computer vision. So vision is not solved, and that will be the focus of my, maybe not just the next 3 years, perhaps my entire career. So what's the next question? The next question is, okay, how do you find a research topic?
No, a research topic that can be published as CPR.
Well, I don't think publication should be the ultimate goal. Publication should be the starting of your research outcome, not the end of a research outcome. The life cycle of your publication just starts after it is published. So I hope you set this as the expectation. And then I will still answer the question of how to choose a research topic, and hope you will make it into a publication. So I think the most important criteria is your curiosity and your passion about the problem. So I think curiosity is the fundamental reason for humans to advance science and for humans to explore unknown problems. And I don't care about the publications. I just care why this problem behaves like that. I just care how can I solve this problem. If I discover it, then there would be a publication. And if I don't solve that, then okay, maybe there would be an incremental publication, but that doesn't matter. So curiosity and passion. And I think that would be the focus of our research career.
Yes, please.
I heard from your MIT job talk that you're going to do some AI for science. I'm personally from a chemistry background and PhD training in computer science here. I'm really fortunate that I have 2 years training. And I'm really interested, like a lot of people from science part, they're learning AI, and then they try to use these models to do some research. And then people from computer science part, they also collaborate with science people in public paper. And what's your opinion on this area? It's a pretty new area.
Yeah, I believe AI will be a fundamental tool for basically every area. Well, the analogy would be like if you go back to maybe 40 or 50 years ago, then there was basically no computer science department. At that time, maybe you need to learn something about computer science in the computer science department. But now you think about today, basically every single discipline is related to some kinds of computing. Computer programs, simulation, data, analysis. So computer science is basically a tool for basically every discipline, every area today. So I'm predicting AI will be the next CS in the next maybe 10 or 20 years. AI will be the fundamental tool for basically everything. So maybe you don't need to have an AI degree, you don't need to enter an AI department or sub-department to learn something about AI, but you will be using AI to discover new patterns, new behaviors, new phenomena from your scientific problem. I'm very interested to make this happen. And that's my goal and my expectation of AI for science.
For that part and some maybe specific applications on that part, I know that for maybe some biological data, the data amount could be small and the quality may be low. And what do you think of that?
Mm-hmm. Well, big and small are relative. So for example, maybe if we think about the image data set maybe 10 or 20 years ago, they would be, today's standard data set would be huge at that time, but they are pretty small today. Then I think, well, it is the size of the data and the related algorithm, they help each other and in a spiral way. That means if you have some amount of data, then you develop algorithm for them. And if you see that your algorithm can benefit from more data, then you may start to collect more data, and then you improve your algorithm on top of new data, and so on and so forth. So yeah, then I think it is a problem of both data and algorithms.
Thank you.
Thank you, Professor Xue's questions and Dr. He's talk. And I am very interested in the key success of ResNet, because I see that the key success under the ResNet is maximally maintain the signal. I am working on building photonic neural networks, and I find it coincides with the analog computing that we should maximally maintain the signal intensity. And I think they are correlated. And I think residual learning will have large potential in analog computing. And what do you think about this? Thank you.
Thank you for your question. So, yeah, I'm not sure I understand the question correctly, but my comments would be like, so today's artificial neural networks were inspired by biological neural networks at the beginning. But then after that, these two directions diverges. So artificial neural networks were specifically designed for some applications or data sets, and then the later components may not have their biological origin. So operations like residual connections and many other components, such as normalization operations, can be viewed in this category. But interestingly, actually, there are also many research in parallel that is about mapping the connection patterns in the human brains or animal brains. The related research is sometimes referred to as, I don't remember the term, connectomes, something like that. So people have found that in those neural networks of human brains or animal brains, they have found very similar pattern to our today's best artificial neural networks. The patterns include long-range skip connections, recurrent connections, and other type of, feedback connections in the neural network. So I think artificial intelligence and cognitive science or brain science can benefit each other. So discoveries from the human brains can inspire our AI to design new components. But on the other hand, successful practice in AI networks can also inspire scientists to better explain our brains. So that would be my comment.
Thank you. Thank you. Thank you. Thank you very much.
Thank you, Professor Shi and Dr. He. I major in computer architecture and electronic design automation. So my question is about the explainability of AI models. Because I find that, okay, the AI models, they perform very well. They can be the human beings in some metrics. However, how could we interpret the entire behaviors of AI models? So this can make a case that we do not weather the prediction, we cannot give the accurate predictions of our AI models, whether our AI model can become very reliable. So how, I was wondering, how do you see this problem? And your comments, thank you.
Yeah, so that would be my answer to this question. I will ask you a question. So, why do you trust a human driver? So when you take a taxi, basically it is a stranger for you. You don't know him or her. You just know he or she is a human. Why do you trust he or her? Is it because you feel his brain is explainable, or because you understand that, well, usually a well-trained, a well-practiced and experienced human driver will do a good job at a very high probability, empirically? I don't need your answer. Because, well, that would be my question. Then I will also ask the same question. Why do we trust an airplane? Is it because we have sufficient physical laws or mathematical derivations that can ensure an airplane can be flying in the air, or because the airplanes has been tested millions of times in the air holes, or both? So I believe, well, explainability is a really good property. I really encourage people to pursue that. But on the other hand, we need to realize that, well, the successful or the success of our systems is also mostly driven or verified by empirical evidence. So that would be my response and comment.
Hello. Thanks for the inspiring talk, and thanks for the professor. I'm like the researcher on the self-supervised learning before and on video domain. So my question would be like when you have mentioned before that you want to explore the self-supervision on image domain, and we all know that in NLP the self-domain from the words, from the sentence, is like already contains some semantic knowledge. But in image, the pixel only is like straight RGB, like they're straight numbers. Actually, they are not. They are from nature. They have no any like semantic knowledge. So like I'm wondering, like is there any like supervision of just to come from the image? So also how to define this self-supervision? So yeah, that's my question. Thank you.
Mm-hmm. Yeah, I think this is the fundamental difference between language and vision, and this is the main problem we want to solve, and we have not been able to solve. I think the most difficult parts of representation learning is how to do abstraction and compression. In the problem of language, part of this job has been done by human beings. The human brain has done this job. But in the case of images, the inputs from the sensor are much more, natural than languages. So then the models need to do its own job in terms of compression and abstraction. And I think this is still an open problem. Then on the other hand, I also agree self-supervised learning from pixels or images or videos is not sufficient, because if we think about animals, animals can see the world, but animals has other feedbacks from the world too. So they can take actions. They can try to find food, and they want to escape their predators. So they just want to survive. So they have many other forms of signals, supervision, or reward from the environment. And it is not just the vision. Then I think our current vision system is lack of the feedback from the environment. And I think this will be perhaps a next topic for visual self-supervised learning.
Yes, thank you. And I wonder, it's just like the embodied AI for multi-modality like this?
That can be, those are all related topics.
Yeah, thank you. Thank you for sharing.
Thank you, Dr. He. That's a really very inspiring talk, and also the discussion. Thank you. I have one question. How far do you think AI is from being able to do abstract mathematics? Do you think that by going in the same direction that we are going, we will eventually be there, or do you think that there's a fundamental gap between?
Yeah, thank you for your question. I'm not an expert in this direction, to be honest. But there can be two ways of doing that. One is just to train a large language model, and you hope the language model can magically figure things out. I don't think this is a promising direction. But the other direction is that what if you equip the large language model with some, let's say, code? So basically the code interpreter in ChatGPT. So that means you allow the language model to write some code, and the code can perform some, computations or symbolic operations. And then that computation can give the language model the feedback, and the language model can decide which step to do. I think this would be a more promising way. Ultimately, I think this is a very exciting direction. I have been thinking, well, let's think about such a scenario. If we go back to the time of Isaac Newton, if we have all the text, all the data at Newton's time, and we train a large language model at that time, can one day the model tell us Newton's laws? I think that is a very high level of artificial intelligence. And if we can do that, what if we just give them today's data and they tell us some laws that we are not aware of? That's an ultimate goal. Yeah. By the way, I like your course a lot. I learned a lot from your course.
Okay, I'm very glad that you were in my course. Yeah.
Let's have two last questions from the audience, please.
Dr. He, thank you so much for your brilliant talk and discussion. And I just have one general and maybe stupid question. What do you think of the future applications of AI in the discipline of arts and humanities? The reason why I ask this question is that I'm the PhD student from a Department of Anthropology in CUHK. So you as an outstanding AI researcher, I'm very curious about your thoughts related to it. Thank you so much.
So your question is about AI for arts and humanities. Well, I'm not an expert on that. Perhaps OpenAI should answer this question. Yeah. Well, it looks like arts and humanity are very special areas for, the human brains. And I think the question would be, what is the fundamental difference between human brains and basically artificial intelligence? If one day, let's think about if we can physically reproduce our brains, but if we just call it a machines, then those things done by that brain, can we call them arts or humanity, or shall we still call them, artificial outputs? Then, well, I think it is a philosophy question. It is more like a sci-fi question. Thank
you so much.
Yeah.
Let's have one last question more close back to Dr. He's original work. So anyone want to, okay, please.
Yeah, thank you for Dr. He's great talk. And you mentioned that curiosity and passion is the key to make great research. So my question is that how to maintain the curiosity and passion, especially when you find one day I find that my code have bug and I have to rerun all the experiment again, and that will be really desperate, yeah, for me. So how to maintain the curiosity and passion in your research? That's my question. Thank you very much.
Yeah, I think research is about frustrations, failures, depression. It's about all the negative words you can come up with. That's just the reality. If you haven't experienced that, that means you are not doing the best research. That is just the reality. My life was just like that. I was disappointed maybe 95% of the time, and then I spent 5% of my time finishing that paper. Then I move into the next cycle, being depressed, frustrated, anxious, until the next work come out, and enjoy the 5% of the time, and then so on and so forth. That is the reality.
Yeah, thank you very much. I'm very motivated. Yeah.
Thank you, Dr. He and Professor Xie. Professor Xie, please resume to your own seat. And I would now like to invite Professor Mai Hashem to present a small token of appreciation to Dr. He. Professor Shan, please. Could the following guests please join us for one last group photo? Professor Tan Hongqi, Interim Dean of the Faculty of Engineering at CUHK. Mr. Laureates, Associate Vice President for External Engagement and Outreach at CUHK. Professor Pascal Oliver Vontenbo, Chairman of the Department of Information Engineering at CUHK. Professor Xie Tianfan, Vice Chancellor Assistant Professor of the Department of Information Engineering at CUHK. Ladies and gentlemen, that concludes the 2023 Future Science Prize Laureate Lecture. Please join me again in thanking Dr. He.